So basically for all the newcomers, my name is Aleksander Mundjar. I am a third-year computer science student here at the University of Ljubljana. I am also team captain of DragonSec SI, which is a cybersecurity team that competes in CTF competitions, so capture the flag. My interests mostly lie in binary exploitation and memory corruption attacks. This is what I'll be torturing you with today. System security, and I've been dabbing a little in malware analysis lately, but just beginnings. Okay, so last time we covered intro into binary exploitation, so we laid some ground rules of what binary exploitation is and what it tries to achieve and how it works. We've also looked into x86 architecture. I said last time that binary exploitation is not architecture specific, and the only reason we are doing x86 is because I know it best. But oh, we have latecomers. So as I was saying, the x86 architecture we'll be using to better introduce binary exploitation, just because I know it well. So yes, we talked about registers and instructions. Basically, whoever is new, whoever came here for the first time, I will go over these things quickly today, so you can catch up just a little bit. But if you had some experience with assembly language, it shouldn't be a problem really. We talked about stack frame layout. So basically in x86 programming, how do subroutines place their local variables and how does the stack change within a program. So we covered that because that's the basis of stack-based exploitation, which we'll be looking into today. We also smashed our first stack. Basically, the last time we didn't really explain what is going on. We just spammed a bunch of A's onto the stack and saw the program crash. Okay, so today's agenda, recap, basically, that's what I was saying before. We'll be looking at software protections, so things like ASLR, Pi, Canary, Relro, NXBit, and a little bit of shadow stack. We'll be talking about how to bypass each of these protections. Then we'll take a look at ROP, which is return-oriented programming. We'll finish off with some attack patterns. So basically, how does the general attack on the stack work? What are the goals? What are the ideas? What are the patterns? Then we will look at some examples, how that actually happens. And in the end, there's demo. There will be a coffee break in between, so like 15 minutes to stretch your legs, get some coffee. Okay, so recap from the last time. Registers. I'll be writing these registers down and they'll be staying on the board for the whole time, because last time some people said that they were having trouble following which is the stack pointer, which is the instruction pointer, which is the frame pointer, and so on. Where do the arguments go and everything like that. And so I'll be writing them down for you to remember and for the new guys to see how it all works. But the idea is as follows. So we basically have RSP, which is the stack pointer. His job is basically to point at the top of the stack. Always. That doesn't change. Unless we change it during the exploitation. That happens a lot. But in normal execution, stack pointer always points on the top of the stack. We have instruction pointer. This register points to space in memory where our instructions are. So basically where next instructions that are going to be executed are placed in memory. So, okay. Then we have RBP, which is base or frame pointer. RSP in conjunction with RBP, they form a stack frame. So basically, if we subtract RSP from RBP, we get how big the current stack frame is, how many local variables does the current function have. And it always points, so if this is our stack, looks like this, we have RSP always pointing in the top, and then we have RBP that's also always pointing on the stack, but it's always a little bit lower than the RSP. And this thing between them, it's a stack frame. And RSP and RBP, so stack pointer and base pointer, will change frequently. So stack will grow larger and larger, and also it will dissipate. But we can always find the current stack frame if we look at these two pointers. Then we have function arguments. These are RDI, RSI, RDX, and RCX. So I'll just write function arguments. So in 64-bit, so x86 64, the 64-bit architecture, we have registers that hold arguments for the subroutine that's being called, and they are placed in this order in these registers. So basically, the first argument is in RDI, the second one is in RSI, RDX, RCX, and so on. When we run out of registers, which we won't, we basically place arguments on the stack. Okay, then we have the return value, RAX is the return value. So basically, whenever a function returns and it's supposed to return some data, some information, maybe an integer or a pointer, it stores it in the RAX register. So basically, whenever the function returns, the function that called it knows to look for the return value in the RAX register. Everything else is for general use. Okay, this will stay on the board, I hope, for the entire lecture, because if you can't follow these things, if you don't know which register we're talking about, you'll be very confused. So use this to help you follow the lecture easier. Okay, so the last time we also talked a lot about stack frames and what they are. I already hinted at how the stack frame looks in the picture on the board. So basically, what you have to know about stack frames is that whenever a function is called, let's say we have main that calls function 1, and so stack will look like this, let's say, and this is the stack pointer points here, and then this happens. So basically, the instruction call F1 is executed, and the function prolog of F1 will create space for its local variables. So in this scenario, the stack pointer will basically, some value will be subtracted from the stack pointer, and it will be placed higher on the stack. And then at the bottom, there will be base pointer. And this is a stack frame. It's an image there. What you have to know is the RBP is the base pointer of the previous function. So basically, whenever this function returns, so whenever F1 returns, main will be able to collect its own base pointer and continue the execution normally. What I want to talk about a little is the leave and return instructions. For those of you who forgot, what is the difference? So whenever the leave instruction is executed, the current stack frame gets reduced, so it gets destroyed. Nothing gets destroyed in memory, but just the pointers move around. So in this instance, nothing will be up here, and just the stack pointer would move down here. this is it. This is the leave instruction, and the return instruction will pop the value that is on the stack into the instruction pointer. So it will help the program continue execution where initially the f1 function was called. So in this case, in main. Yeah, and of course, before returning, the RAX gets populated with the return value as we mentioned there. Okay, so this was a quick recap. Are there any questions based on anything we were doing last time? If anyone even remembers what we were doing, like follow-up questions before we move on. No? Okay. So today we'll talk about protections. So how they work, what they are, and what is their goal. So about 25 years ago, when there were basically none of the software protections that exist today, exploitation of software was pretty easy. So not a lot of need for creative thinking. And so people decided to build in some protections into compilers and loaders and the kernel and everything to make memory corruption attacks harder to execute. So how do they work? Basically, most of the protections we'll be talking about today are binary specific. So you can turn them on or off however you like it. So the canaries or the pi or anything, you can turn them on because they are compile time protections. But there is one protection that's called ASLR that is system-wide. Basically, we'll talk about all of them separately, but how are they added or removed is basically with flags at compile time. I'm talking about GCC. So for example, when you're compiling a C program, if you compile it without any additional flags, every protection is enabled. But you have flags to remove them, basically. There's a screenshot of the tool checksec, which is basically a fancy header reader for ELF binaries. It reads which protections are enabled, and we see there is no stack canary on the main binary from last time. Okay. ASLR. Does anybody know what ASLR is without reading that? No? So address space layout randomization is a technique that is used to increase the difficulty of performing a memory corruption attack that requires an attacker to know the location of the executable in memory. To put it simply, it just randomizes the addresses that are used inside the binary. So basically, whenever a new a new program is loaded into memory to be executed, addresses like where is the stack, where is the heap, where is the code, it's all randomized. So basically, if we have a primitive of I can control instruction pointer, if we don't know where to jump, it's useless. And this is what ASLR does. It prevents us from running a binary and seeing the base address of the ELF, and then running it again using the same addresses. It won't work because it's randomized. And we can see it with the LDD tool. It basically says here that, for example, the libc was loaded at 2 different addresses when we ran it 2 times. Okay, the extension to ASLR is the pi protection. So it is specific to a binary, so you can compile a binary either with or without pi. So what's the difference? So when we have ASLR enabled, oh yeah, and you can enable ASLR, basically it's a file var something proc something va randomized space, something like that. You have to enable it. disable it for the whole system. There's basically no systems today that don't have it enabled by default, but if you want it gone, you have to change the basically one value from 0 from 1 to 0. Just Google it. Okay, so ASLR randomizes the location of stack, heap, and .so, so shared libraries. While pi, if pi, this is short for position independent executable, if pi is enabled, then also elf base gets randomized. What does that mean? Ah, no. So basically that means that we cannot reuse code from the binary because the offsets, because in the compiled elf binary there is only offsets. So there's no hard-coded physical addresses at which the code will be loaded. So the pi is basically an extension to ASLR. It takes care that everything in the virtual memory space of the binary of the process is randomized. And here's the example. So basically I wrote a program that basically says print the address of main, and then I compiled it without pi, so it's the flag -no-pi, and when I run it 3 times, it's the same address for main every time. But when I compile it normally, so just -o pi, we can see that the address changes every time. And okay, some of you may say, well, we can just brute force the address. Well, yes, but actually no. In real world scenarios, the brute force, there is 2 to the power of 24, I think, possible combinations, maybe more. Basically, you would need, if you're doing this over a network, you would need a few days to do it. And every competent sysadmin or intrusion detection system will pick up on that. So brute forcing addresses is not a viable way to do this. Okay, then we have the canary. We talked a little bit about the canary the last time we were here. So basically the stack canary is used in order to prevent stack-based buffer overflows to reach the return address. So if we look at this picture, let's say we have a buffer somewhere in the local variables that has a buffer overflow vulnerability. So we read into it or copy into it more data than it's reserved. Then we'll be able to overflow the stack. And the canary that's placed just above the return address prevents that. So this is the binary compiled without the canary, and this is the binary compiled with the canary. And the only difference there is this check. So basically, before the printf is executed, so basically before the function even begins, there's a value placed on the stack, the canary, and then right after the function would return, it is checked if it's the same as it was before. And if it got changed, this means that there is probably a stack-based buffer overflow present, and we should abort immediately. This stack check fail function aborts the program immediately. Then we have the NX bit, which basically says stack is not executable. So stack is memory allocated for the program to use, and it was initially read, write, and execute permissions, which made it incredibly easy with the combination of not having randomization to just write shellcode on the stack and then jump to it using some overflow or something like that, and the code would just get executed because the stack was mapped as executable area in the binary. The NX bit basically says, no, if the instruction pointer gets placed somewhere on the stack, abort immediately. And then is also the rel row, which stands for relocation table read only. We'll be looking at relocation tables a few slides later, but basically they're used to map out functions from the shared objects onto into elf. So whenever your program tries to call printf or some other function that is not part of your program, there is some process that resolves the address to that function, and then it stores it basically as a cache. It stores it in a table, and that table, if it's mapped as writable, we can overwrite the addresses there and basically can point any function. So basically we can point printf to any other function in the of our choosing. Basically we can point it to system and then print out bin.sh, which results in us spawning a shell. Okay, so for every protection there's also a bypass. ASLR and pi are basically bypassed by us leaking memory. So if we are able to leak an address, let's say that the program is written poorly and we have a for loop that is just writing out data to standard out and there is no boundary checks, and we write some memory address onto the standard out and then read it. With that, we've just leaked some memory address, and then we can map out everything that's on the same page, basically on the same kernel page. I think in Linux that's 4 kilobytes of data. So let's say I leak one address in the 4 kilobytes of space, then I can calculate every other address in there. This is because of ASLR. ASLR is done by kernel page, so every kernel page gets randomized separately. And so if we leak one address from one kernel page, we have the whole kernel page mapped out. The NX bit can be bypassed by simply mapping a new memory page that is executable and jumping there. Canary can only be beat if it gets leaked, basically the same as the ASLR. We can leak it in one function and then reuse it in another. Reuse it how? Basically when we overflow, we put the canary back where it's supposed to be, because canary is the same for every function in the program. Canary gets calculated when the program is loaded into the memory, gets stored in the memory, and then it's being checked every time. So it's the same throughout the whole program. Full rel can easily be bypassed by hijacking the dlresolve function, which is a function used to resolve the addresses of the functions that are not part of our program. So basically the libraries. Okay, so now we've come to the main part of today's workshop. So we'll be learning about return-oriented programming. So this is the basis of every stack attack that exists. We need return-oriented programming because it allows us to form complex instructions and redirect flow of the program in a way that benefits us perfectly, not just it works sometimes, sometimes doesn't. We can basically program with it. We can do to a program whatever we want. And it's done by basically chaining stack frames, one right next to another. So if we have a stack and let's say here is a return address of some function, and we are able to overflow the whole thing. Then we can place a lot of values on the stack. So let's say basically we place here return 1, return 2, 3, and so on. And if every one of these addresses points to instructions in memory that end with rat, the execution is completely controlled by us, because every time the rat will get called, next address will be loaded to instruction pointer, and we can, in this way, we can basically program. Oh, and these things, so basically R1, 2, 3, are called gadgets. We can find gadgets. I think I have a slide on them. There's tools that can find gadgets. Gadgets are basically, gadget is just a piece of code that already exists in the binary. It's been placed there by compiler. Usually, we haven't written the gadgets, but they are always there, unless somebody really tries to remove them. But that's something else. So this is how gadgets look like. So I've grabbed for the rat instructions so you can see them better. But basically, this is the address of the instruction, and then we have the instructions, and then at the end there's a rat. And we can see that at the end of every single one of these gadgets there's a rat instruction, which means that if we place these addresses on the stack, we can execute a ROP chain, basically jump from this, which does some instructions and then returns. We can return to, I don't know, the one right beneath it, and then return to the third one, return to the fourth one, and so on. And I also have some fancy slides to show how this works. Basically, if we initially start with something like this, and then we have a vulnerable scanf that lets us overflow the stack, we basically overflow everything until the first return address. So I go back, we have the return of the f0 function. So when the f0 function finishes, it will return back to address that's written at ret f0. And we overflow that. So basically there's a vulnerable call somewhere in the code, scanf %s, and we put on the stack a few a's for padding, and then when we reach the return address, we put on some addresses. Basically, I've put here ret 1 to 5, and what happens next? Okay, so first the leave instruction gets executed. So basically the stack frame gets reduced, and right after that we have the pop RBP. So basically this is the leave, which is RBP, and basically it has two stages. The first one destroys the stack frame. Basically it moves base pointer to the stack pointer, so the stack pointer drops. And then we have the pop RBP part, which pops the RBP of the previous function as the main base pointer, so as the current base pointer, so the next function can use it. But oh yes, here we've done something also. You can see that the base pointer, which was here present on the screen, is not anymore. Why? What happened to the base pointer? The second, which part of the leave command? This one. So basically what happened, we have overflown the stack and we've written A's on the previous base pointer. And when the pop RBP instruction gets executed, A's get written into the base pointer and it doesn't point on the stack anymore. It points on address hex 41414141, which is A's, and that's not a valid address. So we basically corrupted the base pointer. That's the whole technique named after that. It's basically stack pivoting. You can, if you write an actual address there instead of A's, you can pivot the stack to some other location in the process memory. Okay, and then the return or the ret instruction gets executed. And because we've put some arbitrary address on the stack, the return will just return there. And it will look like this. And right after the gadget on the return one address is finished, it will try to call ret again. And this will just keep happening. Basically, we move down here. Just another one. Basically, when our ROP chain ends, which is always prefixed with the ret instruction, when the ROP chain ends, there will be no more valid addresses, and the program will probably crash. But at that point, we've already achieved what we wanted. We already, I don't know, spawned the shell, rewrote some system files, dumped malware, something like that. So this, what we just saw, is a ROP chain. This is a ROP chain. It consists of multiple ROP gadgets that are placed on the stack, one after another, and the code on the addresses of the gadgets gets executed and returns back to the stack, and it goes in the loop. With the right gadgets, this technique is very strong. Yes, if the binary is, especially if the binary is compiled statically, so if there's no dynamic libraries and code of all the functions in the libraries is placed in the binary, then gadgets, there's like hundreds of thousands of them. So on the static binaries, this is a very, very strong technique. You have already automated tools that read the binary and spit out the ROP chain that spawns you a shell or that lets you execute code or stuff like that. Yes. The most basic scenario, we'll be looking at that today in the demos, is when you build a ROP chain to call a system bin.sh. This basically makes the binary that is doing something completely different to call system with an argument bin.sh to open your shell. And if this is running on a server somewhere, it basically returns to you the connection of the shell and you can have full access to the system. In the advanced scenarios, basically how a malware works is the ROP chains usually are built in a way that they call the mmap syscall, and they map an entire page of executable memory and then dump some code onto that. And you can have remote code execution in that way, but that's quite a lot harder to achieve. Okay, so we finally arrived to the global offset and the procedure linkage tables. So basically, when I was talking about, swipe the board. Are there any questions before we go to this part about the whole ROP thing? Any questions? Okay, so whenever we have, let's say, a printf call in our code, we don't know the address of the actual printf function yet. We only know that we've dynamically linked a library that possibly has that code in there. So in order to find the address while the program is being executed, there's a procedure that's called basically the resolution of addresses, and it works with the help of two tables. So we have the PLT, so the procedure linkage table, and the GOT, so the global offset table. And so whenever a new function is called, the first thing that happens is here there must be an entry for printf.plt. And this entry is connected to an entry in global offset table. So So basically, and this here points to address in libc.so. So whenever the first time the printf is being called, the program looks in the PLT table, it sees that it then jumps to the global offset table, and there it sees that the address has not been resolved yet. After that follows the call to the DL resolve, which is a function that resolves this actual address and then writes it in the global offset table. It basically says here address. And so on the next calls to the printf, the DL resolve is not needed. We can just look up in the global offset table to find the address to our function. How these two structures exactly work together, we won't be going too much into that. But you can look up some source code. If you just compile a binary, open it in Gdb, and look what happens when printf.plt is called, you will see this whole jumping being done, and then the address is being written. But why I'm talking about this is because sometimes this table here, so the global offset table, is writable. So a common attack pattern is to hijack execution by overwriting this. So to point that to system, for example. And then every time printf is being called, actually a system is the one that's being called. So we can just tell the program to printf this. And if we've successfully overwritten address in the global offset table, then instead of printf, the system will be called, and we will spawn a shell. Okay. Yes. I'll spend as little time as possible on this slide. Basically, these are the attack patterns that usually happen on the stack. They are written in an difficulty increasing order. So basically the simple one is at the top and the hard ones go to the bottom. These are the patterns that happen on the stack usually. So basically ret to win, we'll be looking at that today. That's the simplest one, and that's a proof of concept for the stack exploitation. Then we have the ret to shellcode, which basically implies that we have a shellcode, so basically machine instructions already somewhere in the memory, and then we point the return address there and just execute them. Then we have return to libc, where if we don't want to just keep jumping in our binary, there's a way to actually jump in the libraries. So basically we can execute code in the libraries, and of course there's a lot more code there that can help us reach our goal. And at the end there's ret to DL resolve, which is what I've talked about earlier, where if you craft a lot of different structures, fake structures, and put them in the right place, you can basically trick DL resolve to resolve a function. So basically here there's another step that says DL resolve, and DL resolve uses some structures, and if you can fake them correctly, it's not that easy to do actually. Then this address over here gets tampered with, and you can make it resolve to whatever you want. All of the techniques listed above have two things in common. So they are stack-based buffer overflows, and return-oriented programming, or ROP, is needed in order to exploit them. Okay. Ret to win. So it's not a real thing. It's rather a simulation or a proof of concept for students to learn basics of exploiting stack-based vulnerabilities. And yes, how it works is that you have an obvious buffer overflow in a function, and your job is simply to redirect the code execution to a win function that is being defined in the binary, but it's never being called. So basically the idea is to call the function that's never being called. That, of course, is not a real-world scenario, at least it shouldn't be, but it is a proof of concept to how to get started and how the stack-based exploits work. Okay, so this is the example. Can everybody see that? I hope, I think. Can you see the code? Great. What? Okay, Walmart's got you covered. Okay, so that code is vulnerable. Can anyone tell me where? Where is the vulnerability? Oh yes, and let's assume that there is no stack canary and that pi is disabled. So this program is not a position independent executable. What's the problem? Just shout out which line is the problem. fget, so which line is that? 14. Why is that a problem? Yes, but that's usually not a problem. So yeah, the vulnerability is in the 14th line, but why? Okay, so we have a stack-based buffer overflow because the bases of the numbers don't match. Basically, we define an array of 100 bytes, and then we write hex 100 bytes to it, which is a lot more. A hex 200 is 256 bytes, I think. I'm not sure. But it's a lot more than 100, obviously, because base 10, 16 is more than 10. So, yes, that's the vulnerability. Oh, I always keep going up. Okay, we've already established that. So, what is the plan? So we know that there is no stack canary, and that this is not position independent executable. What does that mean? What does that give us? What is possible? Yes, basically because there's no pi, the elf is not being randomized. So the addresses of win and vuln and main are static. They're always the same. So, and because we don't have canary, we can overflow right to the return address and nothing will stop us. And so the plan is that we smash the stack, we overwrite the return address with an address of win instead of somewhere in main, and then we jump into win and execute binsh and get a shell. Okay, so how will this happen exactly? Just imagine that this array is actually proportional to 100 bytes. It won't be, but I did my best. So basically what happens is that we can see here that we have an array of 100 bytes right on top of the stack, and then at the bottom of the stack is the return address for the vuln function. So basically it returns back to main. And when vuln function will return, it will use this address to know where to return. But we can control it. So basically we can overwrite the return address. I've set the return address of win to be hex A just for demonstration purposes. It's not really hex A, but the idea is still the same. So we smash the stack, we overflow all the way up to the return address, and then we put an arbitrary value in that spot. So in this case, hex A. So when the leave gets executed, stack pointer is pointing to the return address, and then ret is being executed, and we get a shell. Okay. Are there any questions here? I went quite fast to that, but we don't have much more time. We'll see in the demos as well. Yeah, we'll have that in the demos. We will be actually exploiting these two programs. What about here? So, where is the vulnerability in this program? I mean, the function is called vuln, so that could help. Yes. So again, dev gets is the problem. This time it's a lot more obvious what the problem is. So there's again a buffer overflow in the vuln function, but what is different? Why can't we just jump to main? Exactly. So win accepts two arguments, int a and int b. And both a and b have to be set to a specific value in order for system.bin.sh to be executed. Otherwise, it will just return. So what's the plan? Before I reveal the plan. Help yourself with the registers. What do we need to do? I'm not asking how are we going to do it, but what do we need to do? Exactly. Which registers? Exactly. Perfect. So we need RDI to be what? Exactly. So we need RDI to be that beef and B to be lead code. And only then we can jump to win. Okay. So this is the plan. But can we do it in a simpler way? Of course, that would be the first instinct would be, oh, we control the parameters, we can set the parameters, we should do it. But that will take a lot of gadgets. Exactly. So, as you can see, if we know the address of win, we also know every other address of every instruction in win. So the easiest path would be to just jump straight to line 11 in system. We don't need to jump at the start of main. We can jump anywhere in main. And was there a question? In win, sorry. Oh, I was talking. Oh, I'm so sorry. In win, of course. We can jump anywhere in win. We don't need to jump exactly at the beginning. Yes, stuff will break. But no, we do not care, because when the child process gets executed, we don't care what happens to the parent. Okay, but we will not go the easy way, because I want you to see how we can control the arguments to the function in order to set them properly. Okay, can anyone explain me why this will work, or why this won't work? So there's some clarifications. The pop RDI is an address to pop RDI ret. The pop RSI R15 is an address to pop RSI pop R15 ret. Just for some clarification, so we know exactly what we're talking about. Why will this work? What will happen here? So after leave instruction gets called, this will happen. Okay, this is normal. But right after leave, there is ret. And stack pointer is pointing to pop RDI return. So what will happen? Okay. Exactly. So the pop RDI will execute, and which value will be pushed into, will be popped into RDI?
Stack pointer increases,
Decreases increasingly, yes. Exactly. Yeah, because when ret will be called, that's still a part of vuln function. The stack will decrease, and so the stack pointer will actually point to the deadbeef. This is exactly when the vuln returns, but it doesn't return to main as it should, but it returns to our gadget, so to pop RDI return. And now, when pop RDI is being executed, what's pop doing? Pop takes a value from the stack and puts it in the argument, in this case in RDI. So it will put deadbeef in the RDI and then call ret again. So basically this will happen. Pop RDI ret. What will happen then? So we've already established that deadbeef will be placed in the RDI. Well, where will the execution continue? No, that beef will be popped into RDI. So basically when pop RDI is being executed, that beef will be pushed off the stack into RDI. And only then the return will be executed. So it will jump one address further. So in this case, the pop RSI 15, R15. So it will look something like this. And so right now, as this right here, the instruction pointer is pointing at pop RSI, pop R15, return. So we already know that this will be placed into RSI. Why is this 0 there? Why can't there be win address right after lead code? Why is there a 0 between? Exactly. Because we have pop RSI and then pop R15, and only then return. But why do we pop both? If somebody knows. Exactly. No, it's because the only gadget that exists that's popping RSI is also popping R15. So this is dead weight. It just has to be there because there's no other gadget. So we use the gadget that helps us, in this case the pop RSI, but we have to position the stack correctly in that case. So we can't just put the win address right after lead code, because then there will be an address of win in R15 and we'll be returning to an empty address. Okay. And we get a shell. Yes. Okay, so we've made it to the end. Oh, yes, that's not true. Is it true that protections compensate for a buggy code? No, they don't.
No,
Because
you just proved it.
exactly, I wouldn't have a job otherwise. I wouldn't have anything to do. If protections would work, then guys like me would only be sitting in classrooms. So protections can decrease the reach and the impact of an attack, but they cannot prevent it if we are writing buggy code. We've talked about ROP, so basically how we can program using gadgets. So basically code in binary that ends with a rat. We've talked a little bit about global offset table, which won't be relevant today, but I just want you to know that it exists. And in demos, we will cover those two examples plus one more to see how it actually all looks in the code, in the debugger and in the memory. Okay, 10 to 15 minutes coffee break. Okay, so before I sit down and we go to the demos, I would just quickly like to go over pawn tools and how we'll be using them. Basically, so I've mentioned pawn tools on the first lecture briefly. It is basically a wrapper around sockets that lets us easily communicate with the process we're exploiting. So in this scenario, let's say we are exploiting process that's called bin, and we say p equals process of something, and this will create a new process from the binary bin, and it will let us interact with it. So for example, receive functions will receive some input from the program. So let's say the program says hello world. We'll be able to receive that hello world and parse it as a string inside Python using ppkreceive. Then we have p.send that will send data to the process. So let's say that after hello world, the process expects us to input some data. There's scanf behind it or something like that. We can say p.send and we will send, or send line or send data or something like that. There's a lot of variations, but they're pretty self-explanatory. But the send family of functions will just send data to the process. And the Gdb Attach is a function that lets us dynamically attach Gdb to the process we're exploiting. So when we are writing complex exploits that have multiple parts and stages and a lot of moving parts, we can examine every single one of them closely as it's being executed. Okay, so I have 3 examples here. Can you see the code on the right? That's the question. Can make it a bit bigger. So something like that. Okay, this is the first binary that we will be exploiting. Can you? Yes. So this one. Okay, let me just make this a bit wider then. Like this. Okay, that includes. Okay, so this is the first piece of code. Where's the problem? And what is the goal? What do we want to do? That's a great question. So I like the thinking. So whenever you encounter a software or piece of code, you first want to know what are the protections. So you don't have to devise a whole complex plan of how we're going to exploit every single thing that exists in the binary and then figure out that none of the protections are on. So we can just jump to shellcode. Okay, but these are the protections. So we don't have pi. So basically everything inside elf, so the addresses of vuln, of main, and of win are known. We can find them. And also there's no stack canary. So what's the plan? Come on, come on. I know you know this. It's yes, gets. What is gets? Do we know gets? Bugs. It should say somewhere here, never use gets. The first line. So gets or get string is basically the same as scanf $S. It reads a string from the standard input and places it on the pointer in its argument. So in this case, in the array. Okay, this is the problem. What's the goal? What do we want to do? Exactly. So how are we going to do that? Okay. Is win being called anywhere in the program? Exactly. So the first thing we have to check is whether win is being called anywhere. And we can see that it's being called inside this if statement. So if the passcode is equal to that beef again, then we will call win. So, oh yeah, this will be a problem. Let me just still be a problem, but a little less problem now. So we have two options. We can just keep running the program until passcode magically becomes that beef, which I don't think will happen very often. So the plan is to overflow the array and change the passcode. Okay, so
The last lecture,
yes,
you showed that the GCC reorders the local variables if you have a buffer. So
yes,
is this true here, or
yes, it is. But I have a deal with GCC not to do that. Basically, there are some optimization flags you can set in order to tell GCC don't touch my variables, because honestly, if we ask GCC to compile this program, it will just say return 0 because optimizations, he doesn't care. Okay, so the idea is to overwrite that beef, and we don't have the canary, so I have here the solution, but I won't show it yet because or I will just for a point to it. Okay, so we see here the solution basically says open the process bof1, attach a GDB session to it. We'll be doing that so we can actually see how the overflow happens. Then we have some padding, and then we have our dead beef. Oh, I forgot about the p functions. So p64 and p33 are just the functions that reverse the endianness of something. So if I call p33 on a number, it will make it 4 bytes long, and it will reverse the endianness. That's what p33 and 64 functions do. So basically, the 64 version, it makes it 8 bytes long and also reverses the endianness. Okay, so if we, okay, should just run it first. Segfault, as expected. Okay, that's not gonna work. Let me just try this again. Set the breakpoint where it actually is gonna hit. No. Well, basically, it works too well. So what is going on? Basically, when we are running the exploit, the GDB session is automatically getting attached to the running process, and I just want it now to break at the end of vuln. Oh, but it won't because of the compare. Yes, of course. I'm not using my brain very well. Okay, good. So I've set the breakpoint now to the compare instruction, where if I do this and increase the font a little bit. So this is the code of the vuln function. And we see by the little arrow here that we are currently at the compare something something, comma, that beef. So the comparison is, so the first argument of the comparison is where, based on this. What does this mean? Do we remember from the last time? So we have RBP, which is the base pointer, and some offset of the base pointer, 4 bytes. So where is this memory region? Is this heap, stack, elf? Where is this? It's stack, exactly. We can easily check that if we say examine RBP and then, I don't know, examine RSP. See, the addresses are the same, just differ by hex 10. This is because of function prolog, which creates the stack frame. Okay, and now if we dump the stack, let's say RSP, what do we see? What's on the stack? So I want you to focus on this first line. This is it, because stack is only this big because of the prolog. So base pointer is here and the stack pointer is here. They only differ by 16 bytes. What's on the stack? And where is the passcode variable?
If you compare passcode, you can see that it's RBP minus x4 because it's the if statement.
Yes. So we can just examine that. Let's say examine gx and say RBP minus 4. Okay. So if you remember from the last time, endianness, so the first byte, so the 2C is not this one, but it's this one. So where does the RBP minus 4 point to? Or the otherwise, will this check go through or not? Will the comparison work? It should, right? I mean, I don't know either, but it should. I mean, nobody said just check. I can just say next instruction. Let's see what happens. So call win. So I guess the check went through. So we are calling win. Let me just do this again. So basically we have the solution script that basically says, I'll be putting, I don't know, it's 10, it's probably 10. It should be 10 A's. 10 A's and then that beef, because we have an array of 10 bytes, and then right after it is a passcode of type integer. How many bytes is integer in x86 64? 7, 8, 4. Yeah, should be 4. So int is 4 bytes, and that's why we have these 4 bytes here, and then we just send the payload to the process. And if we run this again, let me just increase the font a little bit more. Look at the vulnerable function, set a breakpoint at the check again. Okay, continue. We hit the break. We look at the stack. These are our A's. So basically, this is the 10 A's. There's 6 plus 4. Yeah, this is the 10 A's. And then we have that beef on the stack. So we've successfully overwritten our passcode variable. Any questions? Is anything weird? Does anything not make sense Am I going too fast? Is this too easy? Talk to me. Otherwise, we'll move on to the next example.
But we could also overload the return address.
Yes. Because if we run the program and say a lot of A's, a seg fault will happen. This is not because of the comparison. So we override the return address, but we don't have to. But yes, we could, and we will. Just not in one. Okay. Okay, let me just make this a little bigger, like that. Okay. So we have a new binary. So this is the one from the slides, the first one. So we already know what the plan is here. So we can still override the passcode, but should we do it? We get nothing from overwriting the passcode. It will just say, try harder this time. So what should we do? Yes, so we need to override the return address to point to win. But first, let's see what checksec has to say. And yes, we don't have pi, so we see that the default address the binary gets loaded at is x4, yes, this one. And we don't have canary. So yes, the plan will work, should work, is possible. Let's take a look at what the solution script says. Yes, so here is the win address, which is some address. Then we have payload, which is 120 times A, and then the win address. But how would we figure any of these numbers out? So let's say you don't know this. What would you do to get these numbers? So the address and the offset of exactly. So we can use Gdb. We can say Gdb bof2, and then we can just say disassemble which function? Which one do we want to know? Win. And here are the addresses. So we have, this is the beginning of the function, so 6, 4, 7. Okay, and we take this, we copy it, and we say, okay, now we have the address, which is the same, it should be, right? Yeah, it's one of the push. The push base pointer doesn't need to be there because of the stack alignment. We will talk about that when we hit the wall of move APS instruction that needs an aligned stack. But yes, the address is correct. What about these A's? How could we do that? So we used Gdb to find an address, to find the address of win. That's always the same because there is no pi. And now we want to find this offset. I've already found it, but I want to teach you guys how to do it. So what would you do? Where would you start? Okay, so Gdb is our friend again. Yes. Okay, we will set a breakpoint at vuln and say run. And when we hit the vuln function, we want to let the, so let me just start like this. We want to, where do we want to break to know exactly how much to overwrite? So here we have call fgets, and right after that. Okay, let's see. Let's say break here. Continue. Okay, so it says, tell me a joke. All right, I will tell him a joke. I will write 1, 2, 3, 4, 5, 16 A's and a B. Okay, so now we've entered some values for the fgets to read, and we've hit the breakpoint right after that. What now? Dump the stack. So we say 10gx rsp. Oh, look. There's our A's. There's our B. And a new line. So how do we know how large the stack frame is? I only dumped some of the data on the stack. Okay, so the stack pointer is here. This is a stack pointer, and we want to examine the base pointer. Base pointer says dbf0. So if we say 20, this is our base pointer. Do we agree on that? Stack pointer is db80, and dbf0 is the base pointer. So how large is the stack frame now? Or where is the return address? Where is our target?
So we take this pointer, subtract the stack pointer, and probably add, so minus 4 or minus 8.
Yes, exactly. But I don't do maths, so I'll just look here. So basically at the beginning, right after we right before the function starts, there's the prologue, and in the prologue it is exactly subtracted the size of the current stack frame. So we don't need to count or calculate anything. We just look here. But that is, if this is the offset, so let's say I type, I don't know, Python and 70. This is, oh, not this, 112. Why is my offset 120? Why is it not 112? Because we see that the stack frame is only 112 bytes long. Why do I have my offset, my padding set at 120? Because of the pointer or pointers? So if we look at the base pointer here, we see that the difference between base pointer and stack pointer is 70, correct. But is this our return address? Exactly. So we have to always take a look at the size of the stack frame and add 8 or 4, depending if we are on 32 or 64-bit. But in this case, we have to add 8 bytes because right after the stack frame ends, there's a base pointer of the previous function. So we have to take that into consideration. Okay, so now we have the address and we have the offset. That's it. Now all we have to do is run it, and I have a breakpoint set, so this should work. It never does, but let's say it will now. Okay. Okay, we've hit the breakpoint that I've set at. So what happened now is I ran the program, and the program we've created that basically sends 120 bytes of padding and then the return address to the fgets of the program. and I've attached Gdb to it. And now we're looking live at the execution of the program after we've smashed the stack. So if we look at the stack right now, it looks like this. Just from seeing this, where is the return address?
Line from the bottom to right.
Here. Yes. And where does it point to? Win plus 1. I wouldn't say GX, I would say, I don't know, 3 instructions. It points at win. So now what will happen? If we are now at the leave instruction. What will happen when I execute the leave instruction? What will happen with the stack? Yes, exactly. And this is the first step, and the second one. To the AAA, which we don't care about, yes. But why? Why will that happen? The previous base pointer. So what happens inside the leave? You already said that the base pointer gets moved into the stack pointer, and there's part 1 and part 2.
You pop a base pointer.
Exactly. So we squash the stack basically, and then only, okay, I can't really show it because you cannot just execute half of the instruction. But what will happen is stack pointer and base pointer will both point here. So I can just do that. I can just say, here we go. Oh. Okay, so when the first part of leave gets executed, both stack pointer and base pointer will point here. And now the pop base pointer will get executed, and then the base pointer gets populated with A's, and only then the function will return. So if I say next instruction, and I look at the stack, what is on the top of the stack?
Instruction pointer.
Our future instruction pointer, yes, but where does it win? Exactly. So if you look at the address, it's win. And what is the value in the base pointer? A's, as expected. So what happened is we've popped the previous base pointer, so the base pointer of the main function that we've overwritten with A's, and it's right now being the main base pointer, so the current base pointer, which doesn't make any sense. And this would cause problems if we were to pivot the stack. So basically, because of the, just a quick thing I can show you, how does this work. Basically, if I say needs one. I'll tell you about the pivoting stack next time because I need a little bit more preparation. But yeah, basically now that we control the base pointer, we could pivot the stack. This is a known technique whenever we want to build a ROP chain, but we can't do it on the stack. Let's say we are writing somewhere in a global variable or something like that. We can, if we know the address of that global variable, we can pivot the stack to that global variable and ROP there. That's also possible. And that's how it's done, with the base pointer being overwritten. Okay, but now we have to execute the return instruction. And as we've seen on the stack, the top address is the main instruction, the main address. And now when I say next instruction, we see that we are in win. And if I go a little further, we will be calling system with bin.sh. So we've successfully redirected the execution. And if I continue, then the Gdb goes all haywire because I did not tell him to follow forks. but it says here it's executing bin dash. That's close enough for us. Bin bash dash, that's all the same. Okay, and yeah, we have a working shell here. Okay, this was the, are there any questions? This was the part 2. We have one more to go, the final one.
The working shell, right, is that we have kind of shell with privileges of the program that, right, so if that program is kind of running as a root, then when we kind of get the access to the shell, we also have root access in the shell, right?
Exactly. I could also, for proof of concept, put in there, I don't know, puts code redirected, but I wanted to pop the shell because it feels good when you pop the shell. Okay. Now we have the last one. Oh. So we say 3. Okay. So this is basically the one we saw on the slides. I don't have enough space here to show the whole one, but the vulnerability is again in the fgets function. So we read too much data. What I want to focus on is the win. So we have to set the registers. As we said before, we have to find the gadgets, and I will show the gadgets now, and then place them correctly in the correct order on the stack in order to execute a rob chain. So if I cat the solution script here, it's a little bit longer, but it shows nicely what's going on. So, okay, we spawn the process, then we attach the GDB. The padding is 88. We figured that out the same way as before. We found the addresses to the gadgets. We will do that together. And then we crafted the payload. So first we have the padding. This is the padding to the return address. Then we have the pop RDI. And after that, the dead beef. So basically we are popping dead beef into RDI. Then we're executing return again, which returns to the pop RSI and pop R15. We pop these two values into the registers, and then we return to win. We will see that in GDB. It will make more sense then. But before that, I want to show you how the gadgets are found. So basically, there are automated tools to do that. Don't ask me how to do it by hand, because you shouldn't. If I say like that. Okay, here are the gadgets. And let's say I want pop RDI. Oh, grep. I'll just grab for pop. There shouldn't be many of them. Okay. So here is the gadget. It says address 783. So 400,783 is the address of the pop RDI return instruction. And if we look at the here, 783, 400,783 is the same. This is the address. And we do the same for the, it should be here close by. Oh, okay, it's down here. So down here is the other gadget, the 781. And here's the reason why we didn't just use pop RSI return. Why is there's the pop R15? Because it doesn't exist. It doesn't exist. If we grep for the RSI in the output of rob gadget, we only see one match. It's the pop RSI pop R15. So we just say we're gonna use this. It works fine. Okay. So, oh yeah, here is also the gadget rat. This is very confusing because it basically, what it does, it has no effect on the execution. It just changes the stack. Basically, it lowers or it decreases or increases the stack pointer. Because if you just stack up, I don't know, 10 times this address on the stack, nothing will happen in the rob chain. Just stack will be progressively lower because of the nature of the return instruction which pops data off the stack. And it could be sometime used for stack feng shui, as it's called. It's a technique to basically reorder the stack in a way that perfectly fits us. And I used it here because sometimes there are problems with stack alignment when calling functions like system. Okay, but now let's go to the good stuff. So we say Python sol. Okay, and we have the dynamically attached GDB. We make it a little bigger. Okay. Info breakpoints. We have a breakpoint. I don't know if it will hit. Okay, that's great. It hit the breakpoint. Okay, so as it is, as of this moment, we are at the end of the vuln function. So at the leave instruction, and if we look at the stack, what do we see? I'll make this bigger because this... What is happening here? Can anyone map out what's going on? What is what on this stack? What is going on here? This is our input. This is our payload on the stack. So this one or this one? Okay, so this is what? This should be the address of what? First gadget, that is this one. Probably. So this should be 783. 783. So this is the address. We can even say examine some instructions here. This is our gadget. Pop RDI rat. And if we look at the next one, say, I'll just change it one. Pop RSI, pop R15 rat. This is what we'll be executing. And then what is this? Is this our value or is this randomly on the stack? It has a similar address, yes. Are we missing any gadgets? So we have the RDI, pop RDI to set the first argument, and we have the pop RSI to set the second one. Are we missing any gadgets? Probably not. So what comes after the gadgets? What's the last thing that happens? Where do we want to jump? To the win function. So if everything is correct, this should be win function. And it is. Okay, so now we will step through this. I just executed leave instruction. And if we look at the execution tree, we will see that as we executed the leave instruction, the only thing left on the stack is our gadgets. And now we will execute, okay, now we executed return, and we are now at the pop RDI instruction, this one. And if we look at RDI, RDI is set to 1. And our stack, oh, I executed shit. Okay, we executed pop RDI and is now, oh, did we? We should execute pop RDI. Code. Oh, let me see. We executed pop RDI, and there is dead beef in RDI. If we look at the stack, we will see that on top of the stack now is the lead code and the 0. And if we look at the instruction pointer, we'll be executing pop RSI and pop R15 instructions. This will take care of these two addresses. It will pop them off the stack. And the next one in order is this. So if we execute this, pop RSI, pop R15. If we look at RSI, we have the value of lead code. RDI is beef. R15 is 0, but we don't care. And now we execute the final return instruction. which will jump to win. And if we disassemble win, we will see that comparisons are happening with that beef and lead code from registers RDI and RSI. This is the, so it's not, so RDI and RSI here. It's EDI and ECI because they are mapped as integers. So the compiler is smart and doesn't need to waste the entire register. And it just basically says, just use the EDI. But as we said in the first lecture, EDI and RDI is the same thing. It's just a smaller register. Okay, so we've set everything, and if I now let the thing run, we execute a shell. And if we go here, we have a working shell. Are there any questions?
So what if we don't have a nice system call in our code? So is there, I don't know, any other chance that we could kind of plant into system call or something similar? So
Oh yes. There is a lot of ways to do that. Basically, I'll just return quickly to the slides. There is a technique that I've shown here, the attack patterns. We've been doing this. This only works in an imaginary world of believing binary exploitation is easy, and we have a win function planted for us. But this one deals with the same problem, so the binary is exactly the same, but there is no win function. And in this scenario, the plan is to first leak libc, so we know where the functions inside libc are, then go back to main, reuse the buffer overflow vulnerability, and craft the ROP chain that will jump into libc and use the system there directly. That's also possible. And this one here is even more brutal. This one doesn't include any printfs or anything. So you can basically pawn a binary that only has one system call, and that's read. It only reads data and then returns, and that's it. It does nothing else. And if you are good enough and you have, and the binary doesn't have the protections, so it's not position independent executable and it doesn't have canary, you can make that work as well. And it's basically, I've seen that done before. It's very hard, but yes, it can be done. But just for reference, none of this happens in the real world anymore. All of this is very, very difficult to achieve with the protections, because basically if you have canary and if you have pi, buffer overflows are impossible. There's nothing you can do unless you also have leaks and everything else. But let's say you only have a buffer overflow and every protection is enabled, you won't achieve anything. But if you have a heap overflow and every protection is enabled, then it's a whole other story. So yeah, it can be done if we don't have win, and I'll probably be talking about that the next time. So basically, return to libc will be the next step of where we'll be crafting two ROP chains to do two different things and keeping the program alive and everything like that. Any other questions? Okay, then this is it. This is it for today. Thank you all for coming. Thank you all for sticking till the end. Yeah, I hope you see you next time. Hope I see you next time. It should be in 14 days, probably.